Hello, welcome to another module in this massive open online course. So, we are looking at KKT conditions to solve an optimization problem. We have looked at an application, a specific application of the KKT conditions. Now, let us look at an example, that is the application and MIMO, optimal MIMO power allocation. Let us look at an example to better understand this paradigm, right. So, what we want to do today is we want to look at an example for the optimal we have to look at an example about optimal MIMO power allocation. Okay. Let us consider the following. Now, consider the MIMO system. Now, remember each MIMO channel can be represented by the equivalent channel matrix. So, we have the channel 1, 2, 1, very simple MIMO channel. Let us say this is our MIMO channel, this is our MIMO channel matrix. Okay. You can immediately see that this is a 2 cross 2 MIMO channel with this R cross T. So, this implies R equal to 2, T equal to 2. So, basically number of receive antennas equal. So, we have 2 receive antennas. So, this implies 2 receive antennas, 2 transmit antennas, so on. And what we want to do is we want to allocate power optimally to the various modes of this MIMO channel. Remember, the modes are given by the singular value decomposition. Alright, these correspond to the channels with the gain sigma 1, sigma 2 and so on. Alright, and we have to allocate the power optimally to these different modes. Let us consider a total power and the noise power. Remember, we also need knowledge of the noise power. Sigma square equals, let us say 3 dB, 3 decibels, which means sigma square equals 2. Okay. And remember, we have seen optimal power allocation, correct. This starts with the singular value decomposition, correct. So, we have log 1 plus pi alpha I divided by sigma log of 1 plus pi alpha I divided by, actually let us start with a brief description of the MIMO system. So, what we have is, let us consider first the MIMO channel. Remember, MIMO, and MIMO stands for, this stands for multiple input multiple output system, which means that basically you have a wireless communication system with multiple transmit antennas and you have multiple transmit antennas and multiple receive antennas. Okay. And so, you have schematically you can represent, and we have seen this before, you have the receiver with multiple receive antennas. So, this is your receiver, you have the transmitter with multiple transmit antennas, and this is the MIMO channel. Okay. And so, let us say we have T or R receive antennas, and this quantity T equals number of transmit antennas. Now, what we want to do is we want to come up with a framework for optimal power allocation. So, remember we have seen the optimal power allocation problem, that is which is as follows, that is we have a total power P, total transmit power P, and we have a set of parallel channels each given by gain alpha I, and we want to allocate the power optimally amongst these parallel channels so as to maximize the total bit rate that can be transmitted across this channel, that is the sum capacity, that is the sum rate of this wireless channel, that is the problem of optimal power allocation. Now, for that first we have to see how this MIMO channel can be decomposed into a set of parallel channels, because only then one can talk about optimal power allocation, correct. So, let us proceed in that direction, first developing a framework to decompose this MIMO channel, this seeming I mean it is not obvious what the set of parallel channels is in the context of this MIMO channel or multiple input multiple output wireless communication channel. Okay. For that, now first realize that, and we have probably seen this before, that is the received symbol vector y is given as y equals hx bar for this MIMO system, where y bar equals y1, y2, yr. These are the r received symbols across the r receive antennas. H, which is now a matrix, times the transmit vector. Remember you have T transmit antennas, so you have T transmit symbols plus N bar, which is the thermal noise samples, additive white Gaussian noise samples at the R receive antennas. So, this is your vector y bar which comprises of your R received symbols, this is your vector x bar, this is your vector n bar, and this is the MIMO channel matrix H, which is now you can see it relates R received symbol vector R to a transmit symbol vector T or transmit symbol vector x bar of dimension T. So, this has to be naturally of dimension R cross T, where R is the number of receive antennas, T is the number of transmit antennas. So, this is an R cross T MIMO channel matrix. And for this MIMO channel matrix, you have the coefficients H11, H12, H21, so on. This one last row first column will be HR1, last column first row will be H1T, and finally last row last column will be HR comma T. So, Hij is the channel coefficient between ith receive antenna. So, let me just write that. Between ith Rx antenna and jth ith Rx antenna and jth transmit, ith receive antenna and jth transmit antenna. And now the key to understand this decomposition of MIMO channel into a set of parallel channels is what is known as a singular value decomposition. Alright, so we will use this technique of singular value decomposition, which we have probably briefly referred to once earlier in the context of optimal beam forming. We will use this construct of singular value decomposition and subsequently demonstrate optimal power allocation for this MIMO, that is multiple input multiple output wireless channel. Okay, and so this is an important concept. In fact, this is an important concept that arises, or this is an important technique, or you can think of an important decomposition that has several applications in the context of signal processing and wireless communication. The theory is general, so this is termed as singular value decomposition. Okay. Now, in a singular value decomposition, what we do is, given this channel matrix H, you decompose this as the product of 3 matrices U sigma V Hermitian. Consider, now for the sake of simplicity, consider this to be an R cross T matrix with R greater than or equal to T, just for the sake of simplicity, although singular value decomposition itself is very general and can be applied for any general channel matrix. We considering, for simplicity, we are considering a scenario with R greater than or equal to T. Now, this matrix U has the following property. You can, this is an R cross T matrix. Sigma is a T cross T diagonal matrix. And V Hermitian is again a T cross T, and this is a unitary matrix. Okay, this is a unitary matrix. Now, U has orthonormal columns, which implies that each column, the columns are orthogonal to each other and unit norm, and therefore, if you perform U Hermitian U, you will get identity. Now, V is a unitary matrix, that implies that which implies that V Hermitian V equals VV Hermitian equals identity. Okay, so V equals a unitary matrix, and further this quantity sigma is a diagonal matrix of what are known as singular values. So, sigma 1, sigma 2 up to sigma t. Okay. Each of these quantities sigma I is non-negative, that it is greater than or equal to 0, and these are arranged in decreasing order, that is sigma 1 is greater than or equal to sigma 2 is greater than or equal to sigma t. So, these are arranged in, it is important to realize that these are arranged in, these are arranged in decreasing order. Okay, and therefore, now you can write it as the matrix H equals U, which contains R cross T, which means it contains T columns, each of size R, U1 bar, U2 bar, so on up to UT bar, which are orthonormal columns. So, this is your matrix U times the diagonal matrix sigma, which contains the non-negative singular values in decreasing order, into the matrix V Hermitian, which contains the rows T rows, and naturally these are also orthonormal since V is a unitary matrix. So, these rows are also, that is, so this is your V Hermitian, V1 bar, V2 bar, Vt bar, these are orthonormal rows. These are orthonormal rows. Okay. Now, in fact, we have seen this earlier. In fact, what we have seen is precisely, if you remember, we have seen that U1 bar, this is the optimal receive beamformer for the MIMO system. When you talk about MIMO, we had mentioned briefly. U1 bar is the optimal receive beamformer. In fact, U1 bar is the principal, that is principal eigenvector, that is eigenvector corresponding to the largest singular value of H Hermitian. Okay. So, U1 bar, if you look at it, principal eigenvector and V1 bar equals optimal transmit beamformer, that is, it maximizes the gain. Okay, optimal receive beamformer, optimal Tx beamformer, this is also equal to principal eigenvector of H Hermitian H. H Hermitian H. Okay. Now, for the parallel decomposition into parallel channels, the MIMO transmission scheme is as follows. Now, let us look at the following MIMO transmission scheme. What is the MIMO transmission scheme? Now, remember, you have y bar received signal vector equals hx bar plus n bar, and we have the singular value decomposition. So, I can write h as u sigma v Hermitian x bar plus n bar. Now, what I am going to do is the step 1, first step, at the receiver I am going to process with u Hermitian. Okay, so I am going to multiply y bar with u Hermitian to get y tilde. So, this is my receive processing. This is my receive processing. So, y tilde equals u Hermitian. Let us substitute the expression for y bar, which is u sigma v Hermitian, that is h, nothing but h times x bar Now, if you look at this, you have u Hermitian u, which is identity. So, what remains is sigma v Hermitian x bar plus u Hermitian n bar, which we will call as n tilde. Okay, because remember, u has orthonormal columns, so it satisfies the property u Hermitian u is identity. So, we have u Hermitian u is identity. So, employing that, we have sigma v Hermitian x bar, which is sigma v Hermitian x bar plus n tilde, that is after receive processing by u Hermitian or multiplying by u Hermitian at the receiver. Now, what we are going to do is similarly at the transmitter, even before transmission of x bar, we are going to employ a pre-processing operation, or what is also known as a precoding operation. Okay, and that is key. So, MIMO reception processing can be done at both ends. One is at the transmitter, at the receiver. The receiver, what operation at the receiver is receive combining or post processing. The operation at the transmitter is either pre-processing or precoding, that is you are precoding the symbols prior to transmission. Alright. So, x bar, you precode them x bar equals v times x tilde. This is a precoding operation. This v equals the precoding matrix just write this as precoding operation. Okay. And now if you substitute x bar equal to Vx tilde, so what you have, y tilde equals u, or u is gone, sigma V Hermitian, x bar is now Vx tilde, so substitute Vx tilde plus n tilde. Now we use the other property V Hermitian V equals identity, since V is a unitary matrix. So, this will become sigma V Hermitian V sigma times x tilde plus n tilde. Okay. So, this will be y1 tilde, y2 tilde, yt tilde. In fact, just write it out explicitly. So, you have y tilde equals sigma times x1 tilde, x2 tilde, that is the original symbols before precoding, which is what we are interested in, plus you have your n tilde vector. Now, if you can look, now we have a set of parallel channels. Now, this is our set of, now if you observe closely, you have y1 tilde equals sigma 1 times x1 tilde, y2 tilde equals sigma 2 times. So, this is our set, this diagonal matrix in fact is nothing but our set of parallel channels, that is. So, singular value decomposition is what gives us our set of parallel channels. In fact, you will observe something interesting. The gain of the first channel is sigma 1 square, that is alpha 1. Gain of the second channel is sigma 2 square, alpha 2. Gain of the last channel is sigma t square, alpha t. And in fact, since sigmas are arranged in decreasing order, this implies that alpha 1, this channel 1 is stronger than channel 2, is stronger than channel 3, and so on. Similar to the paradigm that we have seen in the original optimal power allocation module. Okay. So, the framework for optimal power allocation. So, what we have is we have a set of parallel channels y1 equals, or y1 tilde equals sigma 1 x1 tilde plus n1 tilde, y2 tilde equals sigma 2 x2 tilde yt tilde equals sigma t xt tilde plus nt tilde, and this is your set of t parallel channels. This is the set of t parallel channels, correct. We have, well, if you look at the ith channel, this is yi tilde equals sigma I xi tilde plus ni tilde. Gain of ith channel, sigma is the amplitude gain, so the power gain will be sigma I square. Equals sigma I square, which is alpha I in your optimal power allocation framework. For the optimal power allocation framework, alpha I is sigma I square. And therefore, now if you have expected, that is power allocated to ith channel, that is expected magnitude xi tilde square equals pi. What is pi? This is power allocated to ith stream or ith channel, this is the power at which you are transmitting symbols over channel I, that is again sigma I square, which is alpha I. And noise power we already seen, that is sigma square. Now therefore SNR of ith channel equals, well, Pi alpha I, which is sigma I square divided by sigma square. The rate, maximum rate of ith channel is log to the base 2, right, log to the base 2 1 plus Pi sigma I square divided by sigma square. So optimization and sum rate will be sum across all the T parallel channels. This is the sum rate of the system. The maximum sum rate will be when you maximize this, subject to the power constraint, that summation of I equal to 1 to I T Pi is less than or equal to P. This is your total power, or this you can talk of this as total power constraint, or you can say summation of Pi equals P. This is your total power constraint, Pi greater than or equal to 0, or rather minus Pi less than or equal to 0, that is vector P bar is component wise less than or equal to 0. This is the non-negativity power constraint, and we have already solved this problem. Pi or Pi star, this is given by the water filling power allocation, that is 1 over nu minus sigma square by alpha I plus, where plus indicates that it is the same quantity if it is greater than or equal to 0, if it is less than, that is this is equal to the maximum of 1 over nu minus sigma square by alpha I comma 0, which is nothing but if you substitute for alpha I as sigma I square, that is the sigma is the singular value, ith singular value, this is 1 by nu minus sigma I sigma square divided by sigma I square plus, this is Pi star. This optimal power allocation allocated to the ith mode, these are known as the modes of the MIMO channel. Optimal power for ith mode of MIMO channel. Okay. So thus what we have shown is that the same water filling paradigm, and now this is, remember, this is nothing but the water filling power allocation. So the same water filling paradigm, okay, the water filling optimal water filling the water filling power water filling technique can be used for optimal MIMO power allocation. So thus water filling thus the water filling technique can be employed for optimal MIMO power allocation. And if you observe that these channels, the parallel channels, are already arranged in the decreasing order of gain. So sigma 1 square is larger than equal to, greater than equal to sigma 2 square, greater than equal to, so on until sigma t square. So naturally first channel is allocated a larger fraction of the power compared to the second channel, compared to the last channel. And there might be some channels, remember, which are below the water level 1 over nu, which are not allocated any power. And in fact the technique to find the nu, the Lagrange multiplier nu, is through the total power constraint, correct. 1 equal to 1 to T sigma square by sigma I square plus equal to P. Okay. Solving this, so you solve this, so solve this equation, solve this to obtain nu. So, this is the framework for optimum power allocation. So, the key idea here is that you use the singular value decomposition to decompose the MIMO channel into a set of parallel channels with the gains given by the squares of the singular values, and naturally once you get these alpha i's, one can use the Waterfilling technique for optimal power allocation given total power P and noise power sigma. Alright, so we will stop here and continue in the next lecture. Thank you very much.